invited talk for this afternoon is by Dr. Anup Biswas, who is a colleague, my colleague here at IISER Pune, and a very established mathematician at a very young age. He is already on the editorial board of two very reputed journals, one of them being the Annals of Applied Probability and Pure and Applied Functional Analysis journals. So, the title of his talk today is Recent Developments in the Theory of Generalized Principal Eigenvalues in RL. So over to you, Anup, and thanks for accepting.
Yeah,
at this test.
thank you, Anisha. I guess you can hear me, right?
Yes, I can. We can hear you. I'm
yeah. Okay. Thanks, Anisha, again. And yeah, thank you, for taking this initiative for this virtual math fest. I'm sure many people are making use of it. A bit of apology because I already presented the same thing last week. So those who have attended, there is nothing new unless I say something in addition to which I have said in the last week. So what I would like to discuss is about, of course, what is a generalized principal eigenvalue. Of course, we probably do understand what we mean by eigenvalues, at least in the context of matrices. Now we have a principal eigenvalue, which we can also think of in terms of operators, and there is a way to define principal eigenvalue. But now we have another notion which is called generalized principal eigenvalue. And in what sense this is generalized, and what are the developments? So this is something many of us might have seen, and for classical course in PD or any the first course in PD, we might have seen this. So if you take a smooth bounded domain and you look at this, all these eigenvalues of this operator solving this Dirichlet boundary condition, right? And it's known that there exists a sequence of infinitely many eigenvalues and going to infinity, the first one being positive, solving this eigenvalue problem. Okay, and this eigenpair lambda and phi n's are known as eigenpairs, and the first one is referred to as principal eigenpair. Okay. Now, if you look at it, it should remind you compact operators, but the compact operator has a relation that eigenvalue should decrease to 0. But here, we are saying it's going to infinity. The reason being the inverse of this operator, the Laplacian operator, is compact. So therefore, the Laplacian has eigenvalue going to infinity because the inverse operator is compact. Okay. Now, let me tell you a couple of properties that this first. So in this talk, I'm interested mainly this particular eigenpair, lambda 1 phi 1. Okay. So this first thing is this phi 1 has a fixed sign, whether you take positive or negative. Okay, it has a fixed sign, and lambda 1 is simple. So that means if you look at the eigenspace corresponding to this eigenvalue lambda 1, that is one dimensional. And you also have Rayleigh formula, Rayleigh's quotient formula, that lambda 1 can be represented as a ratio of two functionals. So that you can figure out from here. If you just multiply with the function phi n and take integration by parts, you get to this kind of representation. And when you look at the CC infinity functions, so this is infimum over CC infinity functions, but if you extend the space by h10, then it becomes minimum because the minimum is attained in this space. Okay. So this is another way to characterize lambda 1. So if you want to define lambda 1. Now, suppose I want to move beyond this Laplacian setting and want to understand what happens if I want to replace it with a more general form of elliptic operators. Okay. So this is an operator which is called in divergence form. So this operator is has a specific structure. So you take a positive definite matrix, so Aij, of course, depending on x, and then you look at this vector and then differentiate it. And yeah, that's how it's written. and then C is generally referred to as potential or zeroth order term. So I'll probably stick to the term potential because it comes from a probability theory. Okay, so this is the structure of the divergence operator, and this is the assumption I'm going to impose, that it's called non-degeneracy assumption, that this Aij matrix, it's positive definite and its eigenvalue is never zero. Okay, in fact it's uniformly bounded from below. So C0 is the lower bound of the smallest eigenvalue, as you can see. Okay, so this is the next level of generalization of Laplacian is because if I take this to be identity, this fellow becomes Laplacian here. Okay, now what happens? So for this kind of operator, there is a way to define bilinear form. How do you define bilinear form? You just multiply this guy with a v and throw this derivative on v. So you actually get to this bilinear form, and it is somewhat analogous to Laplacian. So whatever you can develop for Laplacian is the same fashion you can develop for an operator of divergence form. So particularly operator of this form. Okay. So what helps us here is this bilinear structure. Okay, that plays a crucial role to apply. So this makes this operator symmetric, and there are other properties which is analogous to Laplacian. So you just follow the step of Laplacian to get to the results that corresponds to this divergence form operator. Okay, so there is nothing fancy here. So now let's move to a more general form of operator, which is known as non-divergence form operator. So this is the more general elliptic operator where I have Aijx. Okay, now this guy is outside the derivative. So derivative is double derivative is totally acting on u. That's a matrix, and then you multiply the matrix and take the trace. So you get this summation. That's a vector valued functions, and that's a dot product with gradient of u, and then there's the potential and u. So this is the most general form of linear elliptic operators in non-divergence form. Now, the question, of course, if you want to understand how to define eigenvalue, because we don't have any bilinear operator here, so Rayleigh's coefficient doesn't make sense here. So we cannot go to define a quotient formula or Rayleigh's quotient type and then take the infimum over some class to get to the eigenvalue. So that characterization doesn't work. So another way to see this is, can one deal with a compact operator? So can one prove the inverse of L is a compact operator? Yes, that's possible. But the challenges with this is, so okay, let me just say it, what I want to say. So mostly we are interested in, if you recall, mostly we are interested in the principal eigenvalue. So that is the eigenvalue lambda1 having a positive eigenfunction. Okay, so let's say if you're interested in eigenvalues here as well, with eigenvalues having positive eigenfunctions. Okay, now I mentioned that one can apply theory of compact operators and find an eigenvalue. So the extension of that theory is known as the Crane-Ruthman theory. So the Crane-Ruthman theory, what it does is it looks for the eigenvalues with positive or positive eigenfunction. In particular, it looks for eigenvalues with eigenfunctions in a cone. So when you apply a Crane-Ruthman theory, there is a cone that comes into a play. That cone sort of use ordering to that operator. So for example, if I take all the functions, all the non-negative functions, that forms a cone, and we can use that cone to give a ordering of that operator, and then we can apply Crane-Ruthman theory to find an eigenvalue with positive eigenfunctions. Okay, now that's a pretty powerful tool, and it requires a lot of estimate. Okay, and sometimes it's not easy to get those estimates. For this particular operator, actually one can get. But on the other hand, so this is another one, and which is more powerful in some sense. So this a notion introduced by Beresitsky, Nierenberg, and Varadhan in 1996. Okay, so they used a maximum principal technique to define what we call principal eigenvalue and eigenfunctions. So now remember, we are interested in eigenfunctions or eigenvalues having positive eigenfunctions. Okay, so this is our interest. For rest of the talk, I'm mostly interested in eigenvalues having positive eigenfunctions. Okay, and then I want to see how many eigenvalues having positive eigenfunctions. Remember, in case of Laplacian, we have only one eigenvalue with positive eigenfunctions. Okay, only one. There is no other eigenvalues apart from the first one having positive eigenfunctions. Okay, so now something that should come to your mind, because we are looking for eigenvalues with positive eigenfunctions. So in the setting of matrices, this should remind you positive eigenvectors, and that should remind you parent-Frobenius theorem, right? So parent-Frobenius theorem, what it says that if you take a matrix D, entries Dij, and all of them being positive, so then this lambda 1d, which is known as the principal eigenvalue, is the supremum of this mod lambda. This has this particular properties that this eigenvalues has an eigenvector with positive entries, and lambda 1d has a characterization, so infimum over all this lambda such that dv is less than equal to this. And if you take the supremum, so this sign gets reversed. So here it is less than equal to, now you get a greater than equal to. So you remember this characterizations of lambda 1. So this is actually going to be useful in the later part of the talk. In fact, this is something we are going to make use of it. So you see, I can also define the principal eigenvalue with any of these characterizations that we have the last two lines. Okay. Now let me okay, so this is actually the theory of parent. So the generalization of Frobenius was you can take entries that is non-negative. Okay, it could be zero somewhere, but the matrix has to be irreducible. Okay, so that was the extension of Frobenius, and the same thing holds. Okay. Okay, so now we come back to our operator. So this is our operator, and we want to define eigenvalue. So this is what Beresitsky, Nirenberg, and Varadhan did. So they used, so this is the characterizations if you see. So this is the supremum one. It's kind of analogous to the one we are looking at. So you take the supremum over all lambda in R. Okay. So those who are not comfortable with what W2N is, they can just take it's a C2 functions. Okay, this is much weaker than C2, but I mean, you can as well stick to C2. Okay. Okay, so there exists a function, let's say C2, and continues up to the boundary, satisfying this inequality and positive in D. Okay, so both this relation should hold in D. Okay, so this should remind you somewhat a parent-Frobenius type of definition. But also I had another one. If you go back, see, I had infimum and supremum and they coincide, right? Okay, so this is how they defined what they call generalized. So this is where the name came, the generalized Dirichlet principal eigenvalue. Okay. Now, so it has a couple of interesting properties. So one can show that this lambda 1, this fellow here, is attained by a positive eigenfunction. So there exists a positive eigenfunctions phi. You can have a C2 here, which is continuous up to the boundary. Okay, so that is attained. So that means if I put a lambda 1 here, so there would be equality with respect to the phi. Okay, this will be equal, and this is simple. That means if you look at the eigenspace corresponding to lambda 1, that's one dimensional. Okay, so what happens if I change the domain? So if I increase the domain, the lambda 1 decreases strictly. Okay, so this is a monotonically decreasing property with respect to the domain. So this is also it has. And you see this parent-Frobenius type characterization holds. Whether you take infimum, so then you have to look for sub-solutions. So if you go back here, I had super solutions, which is less than equal to sign. So if I take infimum, the sign flips, and I take, here, and I take sub-solutions, okay? And same class of functions, it has to be just positive, somewhere positive inside. You can take, in fact, positive total inside D. And another supremum, but here I want my psi to have infimum positive. So in previous definitions, I had psi positive inside D. It can vanish at the boundary, but here I want, I mean, it's also positive at the boundary. Okay, so even if you take supremum over that class, it all agrees with lambda 1. Okay, So these are, so you can say that these are other possible definitions of lambda 1. Okay, and all three definitions coincide. Okay, now what is the relation with C? So you see the C is a potential term that I have in my operator C. Okay, how it behaves with respect to C. So if I increase my C, okay, so then my lambda 1 decreases again. So if I have another one, C1, which is, let's say, bigger than C in a set of positive measure, then lambda 1 will be strictly smaller than lambda 1C. Okay, so this also, it has another property which is quite crucial and fundamental in PD, which is called extended or refined maximum principle. It says, suppose that my eigenvalue or the principal eigenvalue is positive. Okay, so I take an L for which this is true, then it has a maximum principle. What it means is that if I take any function u, which is a sub-solution in D, and u is non-positive on the boundary, then u has to be non-positive inside. Okay, so this is called a maximum principle. For obvious reason, you can relate it with the complex analysis. And now, okay. So this is called refined maximum principle. Why it is called refined maximum principle? See, in general, in PD, you see maximum principle where it is assumed that C is less than equal to 0. Okay. So this term is assumed to be less than equal to 0, then you get a maximum principle. Now you see, if I take C to be less than equal to 0, my psi equal to 1 is an admissible function, and then you can prove that this guy is strictly positive. So it sort of takes that C less than equal to 0 as a sub case, and this lambda 1 being positive is necessary and sufficient conditions to have maximum principle. So for example, if I have lambda 1 less than equal to 0, you can prove that your principal eigenfunction has this two property, but not it's not negative. So therefore, this is an if and only if conditions to have a maximum principle, and that's what makes it interesting to characterize when you can have a maximum principles, when you cannot. Okay, yeah. Now I would like to understand that what happens if I want to extend the domain D. So far we have been dealing with domains. There's a smooth and bounded, and you can of course relax the assumption of smoothness. In fact, the work of Beresitsky, Nirenberg, and Varadan, they did it for what they call rough domain. So you can take any arbitrary domain, of course bounded, and the boundary should have a certain property. So in particular, ellipsis domain is fine, but you can go even worse, and it should have a certain property, and that can be explained through a probabilistic phenomena called exit time. But anyway, I'm not getting into that. But they did it for bounded non-smooth domain. Okay. Now, of course, the next extension is I want to go for, let's say, unbounded domain. Okay, let's say smooth or all of Rn. So one possible extension is, let's do it for all of Rn. Okay, it's possible to do it for any unbounded smooth domains or non-smooth domains. It's not very difficult. It's kind of routine in some, there are certain tools one has to use, but I'm not going to discuss the possibility for any general unbounded domain. Rather than I'm sticking myself in D equal to Rn. So you take the unbounded domain and try to understand what is the notion of a generalized Dirichlet principal eigenvalue. Now Dirichlet won't make sense, there is no boundary, but yeah, so you can talk about generalized principal eigenvalue, eigenfunctions, and yeah, and so this 5 property that I listed for bounded domains, how much of them holds true when you have unbounded domain. So the thing that I would like to remember is, let me go back a bit so that here, yeah, so this P1, see this lambda 1 is attained by a positive eigenfunctions, and this is the only eigenvalue with positive eigenfunctions. So that is also true. There is no other eigenvalue with positive eigenfunctions. Okay, so lambda 1 is the only one. Okay, so this is what is also holds in bounded domain. Now go back to Rn. So in Rn, so you see, I had characterizations of eigenvalues in bounded domains, and I showed there are 3 different representations for eigenvalues and all of them agree. So these representations were like this. So first one is supremum when I take super solutions, positive super solutions in Rn. And here lambda 1 double prime, here I want my infimum to be positive. So this is one of the characterizations I had. And here I'm taking subsolutions, but then I'm taking infimum of subsolutions, okay? And why I need it to be bounded, that will be clear in a moment, okay? There is a reason you have to impose these conditions, that you take the bounded, positive bounded subsolutions. This will be probably in the next slide, why I have to restrict. But yeah, there are 3 different ways to define principal eigenvalue. Now the question is, which one should I pick? And yeah, and what is the relation between these 3 different eigenvalues I just defined here? Are they equal? What if not? Is there a possible ordering? And yeah, all these questions becomes relevant. I mean, to begin with, if you want to go further with this theory. Now, what happened is that, so this lambda 1, when I write lambda 1, I'm always looking at the supremum over all positive super solutions. Okay, so that's my definition. And why this is my definition is this, that if you take any lambda that lies below lambda 1, there exists a positive phi, okay, p bigger than n, satisfying this relation. That means any lambda below lambda 1 is an eigenfunction, is an eigenvalue. Okay, there exists a positive phi for that. So you see that therefore, unless I impose this particular condition, this infimum becomes minus infinity. Okay, and which makes this quantity sort of trivial. So therefore, I have to impose these conditions that I want only bounded. Okay. Yeah, and you see that there is uncountable. In fact, there is a continuum of eigenvalues with positive eigenfunction. Okay, which is quite, I mean, different. In fact, very, very different for the case from bounded domains when you had only one eigenvalue with positive eigenfunctions. Now you see there is a continuum. Right? So that's the first difference. Now, second difference is if I assume that some sort of growth conditions on this matrix A. So if A grows at most quadratically and B grows at most linear and C is bounded, then I get an ordering between the eigenvalues. So the lambda 1 is bigger than lambda 1 prime and lambda 1 prime is bigger than lambda 1 double prime. So this quantity, these 3 eigenvalues that I've defined, they have an ordering. Of course, it doesn't exclude the situation that they cannot be equal. In fact, this is what happens. There is an example. This inequality, the last inequality here, can be straight. So therefore, they need not be equal. So unlike bounded domains, when all these 3 quantities are equal, this need not be equal. So why I chose, or why it is defined that I should pick lambda 1 is the principal eigenvalue, because this is the largest eigenvalue with positive eigenfunction. That is the reason for unbounded domains, we define lambda 1 is the principal eigenvalue. Okay. Okay. So now, as I said, that this lambda 1 prime, the green one, is less than, it could be strictly less than lambda 1. So I cannot expect equality for this. But how about the purple one and the green one? So that means lambda 1 double prime and lambda 1 prime. And in fact, it is left as a conjecture that, I mean, of course, there is a large family for which they are equal, but it's a conjecture of Beresitsky and Rossi that if you take A, B, C are bounded, then one must have these 2 equal. But the conjecture is still open and we don't know what happens. I mean, we don't know any counterexamples, and neither one has been able to prove that for all ABC bounded, they are equal. Okay, so this is a conjecture. They believe it's equal. Okay, now, so now coming back to maximum principle, you see that for bounded domains, I have said the principal eigenvalue plays a crucial role in characterizing the maximum principle. But now, what would be the maximum principle in unbounded domain, or in particular in Rn? So you take a subsolution. So since the boundary is infinity, you impose a condition that at infinity it is less than or equal to 0. So if the maximum principle holds, then we should have u is less than or equal to 0 in Rn. Okay, so this is something extension maximum principle in unbounded domains, right? You start with a subsolution that is non-negative at the boundary, so boundary is infinity, so then it has to be non-positive at the boundary, so then it has to be non-positive inside. Okay, and the question, of course, we're interested in that just by looking at the eigenvalue or the principal eigenvalues of L, can I say that it has a maximum principle? And in fact, it is not the lambda 1 that characterize the eigenvalue, but the other one. So the lambda 1 prime and lambda 1 double prime. So these two quantity determines the maximum principle. So L satisfy maximum principle if, only if lambda 1 prime is greater than or equal to 0. So it's a necessary conditions to have maximum principle. On the other hand, under the same growth conditions that I have stated before, lambda 1 double prime, if you take positive, then L has a maximum principle. Okay, so now you see that if these two guy becomes equal, which they have believed as a conjecture, so then this quantity lambda 1 prime characterizes the maximum principle. Okay, it sort of becomes if and only if, apart from the 0 case, of course. Okay, so that's the extension of maximum principle in unbounded domain. Okay, now there is another property which I mentioned, that the monotonicity with respect to C in bounded domain, if you increase C, then the eigenvalue decreases strictly, but it doesn't hold true in unbounded domain. So what happened is that if you look at this map, okay, it did not be strictly monotone with respect to C. In other words, one can find two bounded continuous functions, C and C1, so that C lies below C1 and not equal. That means there is a ball on which C1 is strictly bigger than C, but the eigenvalues are same. Okay, so therefore the strict monotonicity property does not hold. Now, so the question can be that when can I say, it has a strict monotonicity? Okay, looking at L or from some properties of the eigenfunctions, can you characterize this property of monotonicity with respect to potential? And why it is important, I'll try to say one line on this, why one is interested in monotonicity. But if you look at it as a fundamental property, so this is what we could be interested in. And then there are two different kind of monotonicity we could think of. Okay, so let's take, so this was introduced in the joint work with Arapostathis and Subhamay Saha. So this is, you take, let's say, C naught plus. So this is a collection of all functions which are non-zero and non-negative, okay, and vanishing at infinity. So you take all the continuous functions which are non-zero somewhere and they're non-negative, cannot change sign, but vanish at infinity. Okay, now we call it, this is monotone on the right at C. That means you add a H from this class, okay, and then eigenvalue, principal eigenvalue decreases, strictly decreases on the right, okay, because I'm adding H, so I'm sort of moving to the right. So we call it a monotone on the right at C. Now, if I subtract H, okay, and it increase, we call it strictly monotone at C. Now, what happened is that the strictly monotone implies monotone on the right. The reason being, one can show that this lambda 1 is a concave function with respect to C. Since lambda 1 is a concave function with respect to C, and if this guy increase, later on the function has to decrease, it cannot go flat. So strictly monotonicity implies monotonicity on the right, but not the converse. There are examples where the eigenvalue is strictly monotone on the right, but not strictly monotone, okay? Okay, so now when this property holds, so this is a question, what's happening? Yeah, when such thing holds, so this is a probabilistic characterization, and just let me try to tell you briefly what it means is that, so you start with psi star, let's say the principal eigenfunction, okay? So you take the operator L and psi star being the principal eigenfunction, You take the log because that's a positive function, so log makes sense. So I get psi star, small psi star. Okay, and so this is a diffusion process. If you don't understand, it's still fine. So this is the diffusion process having this as a generator, whatever it means, but that's a stochastic process. And there is a stability property of the stochastic process that determines the monotonicity property of lambda 1c. What happened is that lambda 1c becomes monotone on the right at c if and only if y star is recurrent, and this becomes strictly monotone if and only if y star is exponentially ergodic. Okay, so this exponentially ergodicity is stronger than recurrent. Okay, that's why the one below implies the one above. But it also has a very nice implication in criticality theory. What happens is there is a criteria known as Agman's minimal growth criteria at infinity. It's pretty popular in criticality theory, and in fact it is used to prove that your principal eigenvalue is simple. That means the principal eigenspace is one-dimensional. Okay. Now what we proved that this, Agman's minimal growth criteria at infinity is equivalent to the operator is monotone on the right. Okay, so there it's equivalent. Okay, so this is this used a probabilistic argument at criticality theory. So this is done jointly with Rapostathis and Devdeep Ganguly. Okay, now let me point out a very interesting conjecture. Okay, it's called Landis conjecture. It was posed in 1960s. Okay, and still open. So what the conjecture is says that you take a solution U, okay, need not be positive. In fact, it has to be sign changing. I'll tell you why. So it just says that take a solution U of this equation, Laplacian of U plus V times U equal to 0. And V is bounded above by Q square, okay? You can take 1, that means Q is 1, no problem with that. Now suppose that for some epsilon, we have U x is less than equal to e to the power minus q plus epsilon mod x. So that is the decay. So you impose the decay of u sort of an exponential fashion, but q plus epsilon. So this is important. So if I take epsilon equal to 0, okay, so let me state the conjecture first. So if I impose this decay, then q has to be identically 0. So that, okay. So now if I take u equal to, epsilon equal to 0, you can take in particular the exponential function e to the power minus q mod x type function to check that there is a non-zero function for which there is this equation has a solution. Okay, so here this epsilon important. Okay, and this is the conjecture of Landis from 1960s. Now, what has happened on this conjecture? Let me give you some cases. The conjecture is still open. Okay, as of now, so there is a little stronger version of this conjecture by Carlos Koenig. You can go to his paper and find out. So, okay, there is a modification of this conjecture. He proposed another stronger conjecture, but neither of them got solved. For n equal to 1, this was settled because this becomes an ODE, and then you can do a lot of things with ODE, and that was settled by Rossi in 2019. For n equal to 2, if we impose this u of mod x is equal to c epsilon times, here it is minus c mod x log to the power half mod x. So it's much worse than this bound, and also that for a large c, if it happens, then u is equal to 0. So this decay is quite stronger than the given by Landis. And this paper was archived last week and by Logunov, Malenikova, Nadirashvili, and Nazarov, where they use some harmonic analysis tool to prove that this actually happens. And of course, estimate on the nodal sets, nodal domains. Okay, now I said that this conjecture holds true for positive eigenfunctions. So we actually this work with Rapostathis and Ganguly, we gave a sharp lower bound, sort of matching this bound for positive eigenfunctions. Okay, in fact, for the operator L, which is more general than this. So if you take a positive eigenfunction, then this holds true. Not only that, if we assume your lambda 1 of this Laplacian plus V, this operator is greater than or equal to 0, then Landis conjecture holds true. So these are the two cases we could prove that the Landis conjecture holds true. Another case is if your V has a compact support, which is also included in this paper, then the Landis conjecture holds true. The way I see it, the only place where the Landis conjecture becomes quite difficult, in fact, I think every other cases can be reduced to this particular case if you assume your V to be positive, okay? So, or positive of outside a compact set. So that is the place where it appears to be more challenging, because constructing green function at that level becomes very difficult. Okay. So this is on the operator. I started with L. I still have like 10 minutes or so, or maybe, yeah. Let me get into some other kind of question. Now, so far I just spoke about a lot on principal eigenvalue of linear degenerate elliptic operators, whatever the L thing I had. So of course the question can be, can we define the principal eigenvalue for other operators following the same technique coming from Berestes, Nierenberg, and Vardan, using super solution or parent-Frobenius type of representation, and look for positive eigenfunctions. Okay, because then you don't have to go for this Rayleigh's type of coefficients, or you don't have to look at the variational forms. And yes, and so for example, one can look for Pucci type operators, which is called nonlinear Pucci operator, which is of great importance because of its applications in homogenizations and control theory. So there is a lot of work done for that. Second is called the P-Laplacian operator, which is degenerate type operator but having a variational structure. For those kind of operator also has, people have looked at it and worked on those kind of operators to study the eigenvalues. Okay, now this is another kind of operator which is known as infinity Laplacian operator. Okay, it's called the limiting operator of P-Laplacian operators. So now you see this operator has a very crazy form. It looks like the second derivative, or the second derivative part, or second order part, looks like gradient of u. Is there a question? Hello?
No, I don't think there is.
Okay. So you look at the gradient of u, and then the d to u, that's a matrix, and then another gradient of u, and then you take the second product. Okay. So this is called the infinity Laplacian operator. Now, of course, the question is why it's called infinity Laplacian operator. Why the name infinity? It cannot be just the notation I used here, lambda infinity, delta infinity. There should be a reason. Okay, let me point out that part, why it is called infinity Laplacian. Okay, so first of question is how this operator came in business. I mean, why it became an interesting operator after all. Okay, so this is what happened. So in 60, I think G. Aronson, this guy, okay, he wrote, I think, 3 papers back to back, 65, 66, 67. And I think I have only read this 2, so I have listed this 2. So what he was trying to do, so it's called the absolute minimizer in a domain. So you take a domain, let's say you take a nice smooth domain in Rn, and you give a ellipsis function on the boundary. Okay, suppose I've taken a domain and prescribed a ellipsis function on the boundary, and I want to extend the function inside or outside without changing the ellipsis constant. Okay, so this is the question I'm interested in, and one can easily give at least 2 functions. It's not very hard. That there are with that property that it matches with the function at the boundary having the same ellipsis constant. Okay, I think it's called Maxian extension or something. So definitely it's not unique. At least 2 you can find. So what question Aronson was interested in, what extra condition I can impose on this extension so that it will make it unique. Okay, So the extra condition that he imposed on this, it should have this, what he called as absolutely minimizing property. That means if I look at that extension and consider a small subdomain, okay, I cannot find a better extension inside the subdomain. So it's a very vaguely, but that's what it means. And when he sort of fixed this extra property on this extension, it sort of made this thing unique. Okay. Now this extension or absolutely minimizing functions is actually infinity harmonic function. So it solves a function, this guy is equal to 0. Okay. Now, of course, it doesn't justify why it is infinity harmonic. To see this is infinity harmonic, you look at the last line here. So if you look at the P Laplacian operator and you let P tends to infinity, the limiting operator is that infinity harmonic operator, and that's how it named this. It got this name, infinity harmonic operator. So this is the extreme operator as P tends to infinity. Okay. Okay. Now from the structure, it has a lot of degeneracy. Okay. And of course it's non-linear, because if you add two solutions, it does not, solve the same equation. You cannot superimpose two solutions. And there is a famous conjecture which is again still open, that if you take an infinity harmonic function, it has regularity C1 1/3. Okay. So in general, this is the best regularity you can expect. In fact, there is an example that has regularity C1 1/3. Okay. So therefore you cannot expect better than this. Okay. In fact, the function is x to the power 4/3 minus y to the power 4/3. And you can show that that solves this equation in whatever viscosity sense. And till that, the best known work is by Savin in 2005 in dimension 2. He could prove that it is C1 alpha for some small alpha. And then later on, Evans and Smart, they could prove that it's everywhere differentiable. So this is, but the conjecture as a whole is still open. And I think probably one of the most challenging conjectures so far. Okay, so that's how this infinity Laplacian came in business. And one can consider an operator in a quite general form. So you add infinity Laplacian, then you have gradient nonlinearity, and then this is C is the potential, and then you look at u to the power cube. Okay, so that's the equation. Now here, why I want u to the power cube? Because this is 3 homogeneous. If you look at, so this guy is 3 homogeneous. In fact, I multiply u by tu, so t to the power cube would come out. So this is a 3 homogeneous or positively 3 homogeneous. Okay, and this is some conditions one would need on H. Okay, let me go a little fast. Now, as I said that, okay, there exists a solution which is not C2. So as I said in the slide before, that you cannot expect your solutions to have a C2 solution. So therefore, what is the best notion of solutions? Because of course I cannot make give a meaning to this equation point-wise sense. So what would be the best way? And this is done by what is called the viscosity solutions introduced by Fields medalist Lyons. And I'm not getting into this, but this is the definitions and how to arrive at this definition. It's possible. So you take functions that touches you from above and below and look at certain equations or inequations to hold. Okay. So you can prove that if you use the classical solutions, it should hold this kind of inequality. And from there you define viscosity solution. Okay. But let's not get into what do I mean by viscosity solution. The point to be kept in mind is when I say a solutions, I mean viscosity solutions, because classical solution does not make sense. So here, as the similar fashion, I define my principal eigenvalue, but the point to be noted here is I want my function psi to be positive in all of d bar. Okay, it's not only inside, up to the boundary. So that's difference from the Varadhan, Beresitsky, Nirenberg, okay, whatever they had done, and D is a smooth bounded domain. And it's not only done by us, it's actually started from this, several work. So there is a work of Bhattacharya, Muhammad in 2012, Jutinian 2007, and later on by Beresitsky and others in 2015. So they all imposed this condition that it has to be positive all the way up to the boundary. Of course, the question is that if I allow it to be positive inside and can vanish at the boundary, whether this fellow would increase or not. Okay, I get a different value because I'm increasing my class of admissible functions, and that part remained open so far. And we settled this question by a joint work with Wang Hung Vo. So this is a function continuous up to the boundary, but positive only inside D. I don't want it on the way to D bar. And this is the characterization for the infimum, because I said there are three characterizations or three different kind of admissible functions. Okay, so this is the story for the bounded domains. The next challenge is if I want to increase it. Okay, there is an open problem here as well. We do not yet know whether this eigenspace corresponding to the principal eigenfunction, eigenvalue, is one-dimensional or not. Okay, so this problem is still unsettled. Okay, in fact, in the simplest setting where you have a is equal to 0. Okay, and that setting also this problem is not settled. Okay, now the question is, if this work to unbounded domains, let's say Rn, what are the challenges? So the first thing was the Harnack inequality, which we are able to prove. So there are two works. The one is archived, you can find in my homepage. The other one we haven't archived. We're planning to do so. But yes, so there we prove that it has a Harnack inequality. Then you can talk about things in unbounded domain. And all these properties of eigenvalues in Rn, we could establish, and then we could look at a semi-linear equation like this, talk about existence, uniqueness, bounded positive solution, stuff like that. Yeah, so these are the recent extensions to the setting of infinity Laplacian, and I think that's it. Yeah. Thank you.
Thank you, Anup, for such a lovely talk. And